Hello, my name is Mad Max. In the last episode, we learned how the Big Bang Theory was born due to our good friend Hubble. In this episode, I want to talk a little bit more about the Big Bang Theory and about the experiments that were conducted to prove that it is true, because it highlights that in science, great discoveries are often made randomly. Now, look at this man. This man is Penzias. He worked at a state-of-the-art microwave antenna built for satellite research. It was built for satellite research, not to prove the Big Bang. Satellite research. However, in 1964, they discovered a strange signal. Wilson, it looks like we're getting a strange signal. Now, like good scientists do, the first thing they thought of was that it was an error, and they tried everything they could to get rid of it. It must be this damn pigeon crap. Wilson, get a shovel. I'm not making that up. That is what really, honestly happened. However, after removing all the pigeon poo from their microwave telescope, they still got the strange signal. We're still getting the strange signal. To understand the signal that Wilson and Penzias discovered, we need a bit of background information and knowledge. When Hubble first discovered that all the galaxies are moving away from us, or the majority of galaxies are moving away from us, the Big Bang Theory was born, because if you turn the time back, the galaxies are no longer moving away, they're moving closer to each other until they all meet at one single point. Due to a process called adiabatic compression or decompression, we know that this one spot must have been incredibly hot. We also know what happens to particles when it gets incredibly hot, because we have particle accelerators where we can look at stuff like this and where we can test stuff like this. And when particles, atoms, are becoming really hot, they stop being atoms. They break apart in their components. So the first part of the puzzle is that we know the temperature that we need to have the first stable atoms. We know the temperature as the first hydrogen atoms ever were born at. That's the first part of the puzzle. The second part of the puzzle is that light is a wave. And also a particle. But it's also a wave, okay? And if you think about waves on a beach, let's use blue for this, right? If you think about waves on a beach, okay? It looks like this. It's a wave. And there are certain characteristics to this wave. But the only one that I care about is what is called wavelength. This distance from here to here, that's one wavelength. Okay? So this wave has a pretty long wavelength. This wave down here has a shorter wavelength. Now you have to understand that we give light, or electromagnetic radiation, right, as scientists call it, different names based on the wavelength. If the wavelength is a couple of kilometers to decimeters, we call it radio waves. If it's decimeters to centimeters, we call it microwaves. When it gets even shorter, we call it infrared. When it gets even shorter, we call it visible light. We then have red, yellow, blue, right? Shorter and shorter wavelength. Then we have ultraviolet, X-rays, and gamma rays. This is all basically the same, right? This is all the same wave, but the wavelength is different. But it's all electromagnetic radiation. It's all basically light. This is the second part of the puzzle. Now, every object, or as a physicist would say, everybody in the universe is emitting electromagnetic radiation. Everybody. This table, my body, my computer, my light, this wall, everything is emitting electromagnetic radiation. If you have a really old light bulb, like a tungsten light bulb, like the ones that aren't sold in Europe anymore, right? It glows yellow. And if you turn it off, if you switch the light switch off, it does not glow yellow anymore. It cools down and then it glows red and then it stopped glowing visibly, right? It still glows. And the reason why it's first glowing yellow and then glowing red is because it cools down, right? If you heat up iron, it glows red. If you heat it up even more, it starts to glow yellow and then it will start to glow white. Now, I am not glowing yellow. I'm not even glowing red. I'm not hot enough. Let's try this again. Now, this table is not glowing yellow, it's not glowing red because it's not hot enough, but it's glowing infrared. This table, my computer, this wall, is glowing infrared. And now, when stuff gets even colder than this table is, or than I am, it starts glowing in microwaves. And then it will start glowing in radio waves. But it will glow. It will emit electromagnetic radiation. Now, why does this matter for the Big Bang? Let's recap what we learned. We know the temperature the first hydrogen atoms had when they came into existence, right? And we know that every single atom is emitting electromagnetic radiation. And a very specific electromagnetic radiation, a very specific signal, right? What radiation it's emitting is dependent on the temperature. So because we know the temperature of the first hydrogen atoms that ever came into existence, right, we know exactly what kind of electromagnetic signal they were emitting. Now we need one last thing to understand why this matters for the Big Bang and how this can help us to prove whether or not the Big Bang actually happened. And that is something called the Doppler effect. That's a final part of the puzzle. You all know Doppler effect. When you hear an ambulance driving past you, you hear that the pitch of the siren from the ambulance changes while it's driving past you. That's called the Doppler effect. Now, not only sound waves experience Doppler effect, light, electromagnetic radiation, is also affected by the Doppler effect. And one thing that can happen, if light is traveling through space that is expanding, it gets a Doppler effect. If light is traveling through space that is expanding, the wavelength gets longer, okay? So, when it first started out, right, when our first hydrogen atoms first emitted this signal, right, it was a wave like this, right? It was a very short wavelength. But as it was traveling and as the space was expanding, this wavelength got longer and longer over time. This is what physicists call redshift. Why is it called redshift? Because in the visible spectrum, red light has a longer wavelength than blue light, okay? Blue light, short wavelength. Red light, long wavelength. It gets a longer wavelength, it's redshift. So, now we have all parts of the puzzle we need. We know the temperature that the first hydrogen atoms that ever came into existence had. Because we know this temperature, we know exactly what kind of radiation signal they were emitting. And because we have theories about how old the universe is based on the rate of expansion, we know how long this light approximately has traveled. So we know what wavelength we should measure today. Okay? This is Big Bang. This is today. We know what wavelengths we should be able to expect today. And if we look into the sky, if you look into the universe with instruments that are good enough, with instruments that can detect tiny amounts of radiation, we should be able to see this signal everywhere around the universe. If we look into the sky with instruments good enough, we can see today signals emitted by the first hydrogen atoms that ever came into existence during the Big Bang. If the Big Bang theory is true, we should be able to see that. And that is exactly what Wilson and Penzias discovered with their microwave antenna. They were looking through the sky, and everywhere they were looking, they found the same signal. It is exactly the signal that was expected if the Big Bang theory was actually true. However, science did not stop there. 25 years later, NASA launched COBE, a satellite constructed for one and only one purpose: to measure the background radiation of the universe in a high resolution. The findings of this mission match the theoretical predictions so perfectly and with such a low error that you can barely see the difference between prediction and actual findings. The COBE mission is one of the biggest successes of the scientific method to date. It shows that science works. But all of this would have never been possible if it wasn't for Penzias and Wilson scrubbing pigeon poo out of their microwave telescope. Thanks for watching this episode, and tune in next time when I will talk about how every bit of matter in the universe, every single one of those elements, is coming into existence.